Imagine we were performing an experiment where we were closing the switch and opening it and seeing how much potential difference we will measure. So in this setup, the switch S is open, and in this setup, the switch S is closed. So we want to see what is the potential difference when it is closed, what is the potential difference when it is open. So before we do that, we are told that we have a battery right here. The long vertical strand will tell us where is the positive terminal of the battery, and this one terminal, this short strand, vertical strand, will tell us the negative terminal of the battery. But we are also told something interesting. We are told that battery has an EMF of 12 volts. So the EMF is represented by this Greek letter epsilon, a funny looking E, and we are told it is 12 volts, right? So now we take our voltmeter, we check the reading on the voltmeter when that switch S is open. When the switch S is open, it means that there is no flow of current through this whole thing because this is an incomplete circuit. And we check the reading on the voltmeter and we see that the reading is 12 volts, which makes sense because we are told that the EMF of the battery is 12 volts. But something interesting happens the moment we close this switch. So the moment we close this switch, such that the external circuit is complete, meaning we have a flow of charge in the external circuit, we realize the value that the voltmeter measures now has suddenly decreased. We're no longer getting 12 volts, but we are getting 4.8 volts. The EMF is constant. So what has happened to the remainder of that potential difference? What has eaten that potential difference? And here is our culprit. Look at that small letter R inside our battery. Look between the rectangle with the dashes around. You find that there's an R there for resistance. That resistance is responsible for that voltage drop the moment you close this switch. So I want you to think of in this resistance as an internal resistance, the resistance inside this battery. Let us explain internal resistance using this analogy. So one morning when you left home, you had 1,200. Got into a car and you were driving from home to the office. Unfortunately, when you got closer to work, there was a roadblock. And now the traffic cop stops you. And in order to pass the roadblock, you must now pay cool drink of about 720. So you had 1,200, you must pay a sort of a fine of 720. This means that by the time you get to the office, you will have less money than the money you had when you left home. So there at the roadblock, you paid 720 and you started off with 1,200. It means by the time you get to the office, you will have about 480. So the roadblock in this instance represent the internal resistance. That is why when that switch was closed, we saw that voltage drop of whatever value that we observed. So the roadblock is like the internal resistance when a charge is trying to get from one side of the circuit to the other side of the circuit. So think of a charge like that car where it's moving from the negative terminal and it wants to get to the positive terminal. and it's going to travel through this whole circuit. But before it even exits the battery, it must now confront the roadblock, the internal resistance, like the traffic cop stopping you on your way to work. And it had an energy of 12 volts, or it had an EMF of 12 volts. Now it needs to pay cool drink, hence it's going to lose some of its electric potential due to the internal resistance. So by the time it has traveled throughout the circuit up until the positive terminal, now we see that it only had an electric potential difference of 4.8 volts. So that is essentially how we can define the EMF as well as the internal resistance. This means that when the switch S is open, we can define an EMF as equal to the potential difference across the terminals of a battery when no charges are flowing in the circuit. Because if that switch is open, as I mentioned earlier, there is not going to be a flow of charge, and hence we will have an EMF. So our voltmeter will measure an EMF. The moment that switch is closed, our voltmeter will measure something called the terminal potential difference, which is the voltage that is measured across the terminals of a battery when the charges are flowing in the circuit. And typically, this is usually much lesser than the total EMF.